this video, we're going to talk about strong induction and well ordering. Strong induction is a little different from the mathematical induction we talked about in the last section. The implication is that it's like a stronger statement. So let's look at how it's different. So they start very similarly. We have two steps, a basis step and an inductive step. The basis step is we start by showing P of 1 is true, or whatever the first case is. Sometimes it's not literally the one. And then the inductive step is where the difference is. So previously, we would just assume that this was true, that just P of K was true, and then we'd show that P of K plus 1 works. But now we're assuming everything before P of K is true. So P of 1, P of 2, P of 3, all the way up to P of K is true. So we're assuming all before, not just K. All right, so let's see how this works in a problem. It's going to be pretty similar. So let's show if n is an integer greater than 1, then n can be written as a product of primes. So this is kind of a basic concept that, you know, people have kind of learned back in maybe middle school, even elementary school, when they first talk about prime numbers. So we were going to prove that as long as the number is bigger than 1, it can be written as a product of primes, and we're going to use strong induction. Before we do that, let's go ahead and let's let P of n be the proposition that n can be written as a product of primes. All right, now let's use strong induction. And I'm going to indicate that, just say strong, and here I'll abbreviate induction. Okay, so first step then. First step in this case is not showing that P of 1 works because it says it's greater than 1. So actually our first number that we're going to be looking at is 2. So P of 2, referring to the number 2. Can 2 be written as a product of primes? And the answer is yep. So this is true since 2 is a prime and can be written as the product of 1 prime. Of 1 prime itself. So we're done because it can be written as a product of 2, and that's done. Okay, now step 2, here's the difference, strong induction. So we're going to assume, now here's how we write it, written a little bit differently. So rather than say assume P of K is true, we're going to say assume P of J is true, but J is going to range from 2 up to K. So we're kind of saying J can be anything from 2 all the way up to K. All of those cases are going to be true. Okay, so let's look at P of K plus 1. So consider P of K plus 1. So first, we have two possibilities, just kind of like what we saw up here with 2. K plus 1 could be prime. So K plus 1 is prime. That's one possibility. And if that's the case, oops, it's so picky about the eraser. I'm gonna have to do backspace, backspace. There we go. Okay, is prime. If that's the case, then we're done. Because just like above, we can say it's a product of 1 prime, which is itself. All right, so the more interesting case is when K plus 1 happens to be a composite. That's the opposite of prime, a composite number. Okay, if that's the case, K plus 1 is a composite, then we can go ahead and write K plus 1 equal to A times B, where A and B are 2 integers. And here, I'm going to write that using integer notation here. Remember, Z represents the integers, and I'm saying that A and B are elements of Z. Okay, so I'm saying that K plus 1 equals A times B. They're integers. And just for the sake of giving order to these integers, let's say that A, oops, not 0, that A is bigger than 2, but smaller than B. And both of those, oops, happen to be smaller than K plus 1. Both of those numbers. So not K plus 1 itself. Okay, so if that's the case, then by assumption, that means A and B can be written as a product of primes because they fall into the category that we created for J. Since they're strictly less than K plus 1, that means they're less than or equal to K. And therefore, since they're bigger than 2, they qualify as the assumption that we just did with J. So by assumption, A and B can be written as a product of primes. Oops, A and B can be written as a product of primes. And then again, we're done because K plus 1 can be written as a product of primes too, because it can be written as a product of A and B. They can be written as product of primes. So that follows that K plus 1 must be also, or can also be written as a product of primes. So it follows K plus 1 can be written as a product of primes as well. So we have shown then that P of K plus 1 is true. And we're done. We have used strong induction to show the two cases. All right, so it's similar to the mathematical induction technique we learned in the last section. We're just assuming more, and it allows us to pull from that a little bit more. And in this example, we needed to pull from it. We couldn't just have one number be work for the assumption. We needed A and B to work in order for us to actually prove this. Okay, let's look at another example. This one's a little different. I kind of like it because it builds on some ideas of how we can use patterns to make assumptions. But again, we have to kind of have this setup where we're working with multiple numbers in order to pull this off. Prove that every amount of postage of 12 cents or more can be formed using just either 4-cent or 5-cent stamps or both. Okay, so we can total up the postage. As long as it's bigger than 12 cents, we can make postage out of 4 and 5-cent stamps. Okay, so before we get going, I'm going to kind of like examine this a little bit before I do that. So here, I'm going to kind of go off to the side. So if I'm going to, here, before I do that, actually, let me start with my proposition. So we're going to say P of N is postage, or the proposition that postage of N cents can be formed from 4-cent and 5-cent stamps. And here I'm going to use the cent symbol. That's the cent symbol. So 4-cent and 5-cent stamps, just for the sake of giving myself a little less to write. Okay, so here I'm going to explore this a little bit. I'm going to come over here to the side, and I'm going to figure out what it looks like for P of 12. That is a 12. Doesn't look like 12. It drives me crazy. All right. P of 12. All right, so in order to make 12 cents, I would need 3 4-cent stamps. Right? Easy peasy. Okay, to do 13 cents, I could do 2 4-cent stamps, that's 8 cents, and then add the 5 cents. So 1 5-cent stamp. Okay, to do 14 cents. Okay, for that one, if I wanted to create, 10 cents, That'd be 2 5-cent stamps. And then I would need 1 4-cent stamp to make that happen. Okay, and then for 15 cents, I need 3 5-cent stamps. Okay, I hope we see a pattern here because I can kind of see something. So I start with 4-cent stamps, and then I moved to, 2-cent stamps. And then I moved to 2 4-cent stamps. And then I moved to 1 4-cent stamps. And now I have no 4-cent stamps in the next step, right? None at all. But at each step, I'm also increasing my 5-cent stamps. So I start with 0 5-cent, and then I go up to 1 5-cent, and then 2 5-cent, and now I'm at 3 5-cents. So if I kept going, P of 16 would be 4 4-cent stamps. And then P of 17, I'll bet, is 3 4-cent stamps. That's 12 cents plus another 5-cent stamp. Okay, so the idea is every time I get to a multiple of 4, from there on, it decreases the 4-cent stamps and the 5-cent stamps start increasing. Okay, that's the pattern. Cool. All right, so now that I got this pattern down, I'm ready to use strong induction to prove this. Okay, so first thing I'm going to do is I'm going to show that P of 12 can be done. So P of 12 works because it is 3 4-cent stamps. Okay. Now, because I want to show this pattern, I'm going to go ahead and show what happens once we get up to 15 cents. So the next step is that I would have 2 4-cent stamps plus 1 5-cent stamp. Then I'm going to go 14 is 1 4-cent stamps plus 2 5-cent stamps. Then P of 15 lands me at 3 5-cent stamps. And then I start repeating the pattern based on multiples of 3. Okay, here we go. So that's my induction step. I've shown that 4 of them are true. 4 of those cases worked out. First case and then the 3 thereafter. Okay, so assume that P of J is true. Remember, I'm kind of doing this weird way of writing it. For J is going to go from 12 all the way up to K. All right. Now, for the moment, K is definitely going to be a number that is bigger than or equal to 15. The reason is I'm going to use what I know about what happens when we have this pattern of 13, 14, and 15. Okay, so I'm kind of picking up from the point where my pattern would start to repeat. All right, so K is bigger than or equal to 15. So we want to look at K plus 1, right? That's my goal. I want to look at K plus 1. So consider P of K plus 1. Now, before I do that, I'm going to cheat a second here. And I'm going to use what I just wrote up here about K being bigger than or equal to 15. Here's what I'm going to do. This is a little tricky. All right. First, P of K minus 3 is true. So I'm looking at 4 cents before this. The reason it's true is my assumption about K. K is bigger than or equal to 15, which means K minus 3 is bigger than or equal to 12. Which means, based on my assumption, it's true. So K minus 3 is bigger than 12. So by assumption, it's true. Okay, now here's why that's useful. If P of K minus 3 is true, that means I was able to make some combination of 4 and 5 cent stamps to total up to K minus 3. So to add up to k plus 1, we add a 4-cent stamp to the total. So to go from k minus 3 to k plus 1, I literally need to add the number 4, which happens to represent in our problem a 4-cent stamp. So if I just add one 4-cent stamp, k plus 1 is now the sum of 4 and 5-cent stamps, because k minus 3 was already the sum of 4 and 5-cent stamps. So k plus 1 is now the sum of 4 and 5-cent stamps with an additional 4-cent stamp. So we add a 4-cent stamp to the k minus 3 postage. And we're done. Therefore, P of k plus 1 is true. And we have shown this works. Wowzy wowza. All right, so we've done it. Now, I want to look at the well ordering property. And this is going to help us prove probably one of our more complicated problems up to this point. Proves up to this point. Okay, so here's the well ordering property. It's kind of simple. Every non-empty set of non-negative integers has a least element. So if we know we're looking at a bunch of positive integers, non-decimals, they're positive numbers, there's always a smallest number in that set. And that makes sense because what we're really looking at is the natural numbers or the whole numbers. And the whole numbers have a different order. We have a less than or equal to thing. So if one happens to be there and it's the smallest one in that set, there you go. There's the least element. Okay. Okay, so let's look at how we can use this in a proof. Now this proof, like I said, is probably the most complicated proof we'll see up to this point. But it's a good exercise in some of the more complicated principles that we can show using the well ordering property. And we're going to kind of combine it with some stuff that we've done prior to this point in this class. All right, this class and even the previous class. Okay, so here we go. Use the well ordering property to prove the division algorithm. So the division algorithm says that if A is an integer and D is a positive integer, then there are unique integers Q and R, where R happens to be smaller than D, and A equals DQ plus R. So this is the idea that if I divide a number like 5, and I divide it by 3, right? 3 goes into 5 once with a remainder of 2. That means that 5 can be written as 3 times 1 plus 2. So there's the thing I've divided by. And here's the two new numbers are the Q and the R, the quotient that we get and its remainder. All right, that's how the division algorithm works. Okay, so now that we see how that works, let's go ahead and try to prove this. So let's break this up into a few pieces here, because this is a little more complicated than you might realize at first. So when it says there are unique integers, there are implies that we have to show that these integers exist. So we have to be given A and D, and from that, we need to be able to find Q and R. All right. And that means that those integers will exist. Then we need to show that R is always smaller than D. Okay. We need to show that they are unique. And then they'll be in this form. Okay. So we're going to actually start with the form. That's the easiest place to start. And what I'm going to do is I'm going to create a set based on this form. I'm going to create a set, which I'm going to basically solve for R here. And I'm going to say R equals A minus DQ. Okay, so I'm going to create a set based on that form. All right, and here's how it's going to look. So first thing I'm going to do here in my proof is I'm going to show existence. I'm going to show that Q and R exist. Wow, that does not look like the word existence, does it? Nope, back up, back up. Thank you. Existence. There it is. Okay, we're going to show that Q and R exist and that R happens to be smaller than D and bigger than 0. Okay, that's what we're going to do first. So we're going to show they exist, and then we're going to prove that they're unique. That'll be step 2. Okay, so existence, here we go. So I'm going to create a set S, and this is the set of all remainders, but I'm going to call them A minus DQ. So I'm not going to call it that. I'm not going to call them the remainders. So it's all the numbers that are in this form, A minus DQ. Okay, and here's what's going to be special about this set. A minus DQ is going to be positive numbers only, and Q is going to be an integer. Okay, so this is what I need this set to look like. These are going to basically be the set of all my remainders, okay? And my remainders, I need them to be bigger than or equal to 0. I need to pair them with Q, which is this other magic integer that I'm trying to show exists, all right? And there we go. Okay, so first thing I'm going to do is I'm going to use the well ordering property. The well ordering property says that if I have a non-empty, non-negative set of integers, there's a least element. So I've made this set by design to be non-negative, right? Because I chose to say that they're bigger than or equal to 0. So there's the non-negative piece. But now I need to say that this is non-empty. So I need to prove that there's something in here, okay? So that's what I'm going to do here. I'm going to say S is non-empty. And the reason it's non-empty is I can make it have something in the set. One way I can do that is I can say if A happens to be any number bigger than 0, bigger than or equal to 0, any number bigger than or equal to 0, if that's what A is, any number bigger than or equal to 0, then what I can do is I can pick Q to be 0. So if A is a number bigger than or equal to 0, if I'm going to let Q be 0 in that case, and what that means then is that A is going to equal, A is going to equal, or I'm sorry, A is going to be A minus D times 0, which is something in this set. Automatically, it's something in this set. Okay, it's in the form, so it's in S, right? It's in the right form. And because A is bigger than or equal to 0, I definitely know it's in S. But now what I've just shown here is that A is in S. So what I have shown is that by assuming A is bigger than or equal to 0, A is going to be in my set S. Okay, now let's consider the other case. What if A isn't bigger than or equal to 0? What if it's smaller than 0? What if it's a negative number? Okay, in that case, I'm going to let Q equal A itself. Okay, so here's what happens then. If Q equals A itself, here's what I have. I have A minus D times A. Now, right now, I'm curious on whether or not this fits into the set S. So in order to know if it fits into the set S, I have to see if it's bigger than 0, bigger than or equal to 0. So this happens to be factorable. And what do I know about A? A is a negative number. But D is a integer, right? It's an integer. And they told us D is positive. Here, look. Boop. D is a positive integer. So because we're given A and D are given to us, D is a positive integer, which means that when I do 1 minus D, this thing is going to come out either to 0 or negative. Either way, then, that means that this thing is going to be bigger than or equal to 0. So A minus DA is an element of S. So it's non-empty. When A happens to be a positive number, it works. When A happens to be a negative number, it works. When A equals 0, it works. So anything I let A be, it's going to end up giving me something in the set for S. Okay, so S is non-empty. Now that I've shown S is non-empty and I created S to be positive, I can now use the well ordering principle. So by the well ordering principle or property, sorry, well ordering property. It's actually called principle or property. It just kind of depends on which book you're looking at. By the well ordering property, there is a least element in S. And we're going to call it R, where R is going to equal A minus D Q naught, where Q naught is my special Q number. A is an integer. It can be anything bigger than or equal to 0 or less than 0. D is a positive number. Q is the other magical number I need to find here. But because I've created this set and I show that this set is non-empty, R is going to be in this form here. So I forced R to be in the right form. Okay. Now here's what I need to show. I'm almost there. I need to show that R is smaller than D. Now I already know that R is bigger than or equal to 0 because this set contains non-negative numbers. So that part is done. I just now need to show that R is less than D. Okay. Once I show that R is less than D, I'm done. I found Q by the well ordering principle, and I found R by the well ordering property. I found them both by the well ordering property from this special set, but now I just need to show that R is less than D, and I've at least done the existence part. Okay, so I'm going to use contradiction. So if I want to show that R is less than D, let's assume it's not. So assume R is bigger than or equal to D. Then here's what happens. That means that A minus DQ naught is also bigger than or equal to D. Here, I'm going to move D to the other side. So A minus DQ naught minus D is bigger than or equal to 0. I'm going to factor out D. A minus D times Q naught minus 1 is bigger than or equal to 0. All right. And what I'm looking at is a positive number. Now, here's what's interesting about this right here. This number, A minus D Q naught minus 1, happens to be less than A minus D Q naught. And the reason is, I'm sorry, I keep saying Q naught, but that's Q sub 0. That's an old thing that my very first calculus teacher, she used to say Q naught instead of Q0 or Q sub 0. And that just stuck with me for the rest of my life. And the reason is this is going to be a smaller number than this, because Q is an integer. And if I subtract 1 from it, it's clearly going to cause that to be true. So if I'm subtracting 1 from Q naught, it's going to make the number on the left side smaller than the number on the right side, period. But this is what I called R earlier, right? That's R. So what I have just shown is that this number right here that I've created is an element of S. And the reason it's an element of S is because this is positive. So it's an element of S because it fits the format. It's a positive number in the right format. And since it's an element of S that happens to be less than R, it's the least element. So we've just shown that this thing right here is the least element of S, or that it's smaller than the least element of S, which is an absurdity. That's not true because R is, by the well ordering property, the least element of S. So we have a contradiction. So therefore, we can assume that R is less than D, and we have now shown the existence. Okay, now to show uniqueness, to show that these two numbers are unique, here's what we're going to do. We're going to kind of do assume that they're not, kind of the same idea, right? But what we're really going to do is say, let's pretend that we are able to write A in two different ways. First with the Q and R that we claim it is, and a different Q and R. Let's call that Q prime plus R prime. Okay, now in this case, what I'm going to do is I'm going to end up showing that Q and Q prime are actually in fact equal. And same with R and R prime. That's what I'm going to do. That's how I'm going to prove they're unique. I'm going to assume it's possible to write it two different ways with two different Q's and R's, but in the end, I'm going to show that, nope, just kidding. They were actually the same Q and R. But before I do that, I have to assume that R is bigger than 0, but less than D. And similarly, that R prime is bigger than 0, but less than D prime. Okay, now I'm going to use this statement here in a second. I'm going to use this, and here's how I'm going to use it. This, you kind of had to work on some stuff to see that I'm going to use what I'm about to use here. All right, but here's what we're going to do. I'm going to rewrite the first integer or first inequality here. I'm going to rewrite it by multiplying everything by a negative. When you multiply an inequality by a negative, what happens is not only does everything turn negative, but it flips all of the inequalities. So this becomes negative D is less than or equal to negative R, which is less than or equal to 0, which has either negative nor positive, right? Okay, cool. So if I multiply everything by a negative, oops, sorry, that shouldn't be. Oh, it's going to get mad if I try to erase it. Please don't jump the page. Aha, it didn't. That's so exciting. Okay. Less than, strictly less than, no equal to. Okay, cool. Now, here's why that's useful. If I combine this inequality with this inequality, I can add those two inequalities together. And here's how that ends up looking. What I end up getting is negative D is less than R prime minus R, which is less than D prime. So I'm able to combine the negative D and the 0 to be negative D. I'm able to combine the two numbers in the middle to be R prime minus R. And then I'm able to add the D prime and the 0, which gives me D prime. Notice though that I keep the stronger inequalities. I keep the strictly less than, no equal to's. Okay, now here's why that's useful. This is a statement about absolute value of R. And this is old school algebra here. If it's been a while, I understand why. Oh, I just realized that's not supposed to be D prime. Oh, I'm going to use the eraser again, and it's going to get so mad at me. Sorry, that's not supposed to be D prime. It's just supposed to be D. The reason is there's no D prime. D is the same in both statements. My apologies. Okay. Oh, I've got to do an eraser again. Okay, such a relief. All right. So there we go. That's more correct. No D prime. I was like, wait, that should be D prime, and it shouldn't. Okay, so this is an inequality statement. We're basically saying that R prime minus R is less than D. The absolute value of R prime minus R is less than D. Okay, so here's how we're going to use that. First, since these two statements are both statements about A, I'm going to come back over here to my initial first thing that I just wrote. So since this is saying A equals this and A equals that, let's go ahead and set them equal to each other. So DQ plus R must equal DQ prime plus R prime. All right, so I'm going to get the two terms that have D's in them to one side and the R's to the other. So this is going to be DQ minus DQ prime equals R prime minus R. Ooh, that's very close to what I just did over here, right, with the inequality. That's kind of nifty. Before I do that, I'm going to factor out D, since they have that in common. And I'm left with Q minus Q prime equals R prime minus R. All right, now I'm going to introduce the absolute value in here so that I can use what I just did over here on the right. I'm going to kind of write it like that. All right, so I'm going to introduce the absolute value. So this is the absolute value of D, absolute value of Q minus Q prime equals the absolute value of R prime minus R. All right, now I happen to know that R prime minus R is less than D. I just showed that over here. Therefore, since this is less than D, this whole thing over here is less than D also. Now, remember, D is a positive number. Remember that? D is a positive number. That was like very long time ago. I even underlined it. D is a positive number. So I don't need an absolute value around the D. In fact, I'm going to go ahead and erase it and hopefully it won't jump. Such a relief. Cool. So I dropped the absolute value around the D. It's not necessary. And I'm going to divide by D. So what I now have is that Q minus Q prime is less than 1. Okay, but if Q minus Q prime is less than 1, and Q and Q prime are integers, right? They're integers, then unless they're both 1, there's no way for it to be less than 1 unless they're 0. It's just, it's not possible. This does imply that they must be 0. In order for this to work, that Q minus Q prime must equal 0, which means Q equals Q prime. Because, I mean, think about it. In order for Q and Q prime to end up being less than 1, we're basically saying they need to be less than a fraction. And it's impossible to subtract any integers and get a fraction. We can subtract integers and get 0 if they're the same integer, or 1. That's the other option, right? But 1 isn't going to cut it. It has to be less than 1. So this forces Q minus Q prime to equal 0. All right. Well, if Q minus Q prime happens to be equal to 0, that actually helps us when I go plug it back in over here. So if they happen to equal 0 and I plug this in up to here, right? I plug that in. What I end up getting is that R minus R prime also has to equal 0. I'm sorry, R prime minus R must equal 0, which again means that R prime and R are the same. And we've done it. We have shown that the integers are unique. And there you go. The hardest proof yet we've done in the class.